Hello everybody. So in the last class of our discussion we were discussing the identical particle, and we came out with two kind of wave functions, symmetric and antisymmetric wave function, right? So now moving forward, and on the further discussion of symmetric and antisymmetric wave function, what we found out in the last lecture, let's have a little recap of that. Because identical particle, in the identical particle discussion, this is very much to understand that there are two kind of wave function, and there are two type of particle which follows those wave functions. Okay, so and from there on we generalized Foley exclusion principle. That Foley exclusion principle is a particular statement which says that for antisymmetric particles we can't have the same eigenstate for two particles. Okay, in the generalized discussion we must have for if I consider the periodic table and any atomic element having more than two electrons, like helium atom and then boron and so on, lithium and all. So to describe the arrangement of electron in different eigenstate, I need to take the Pauli exclusion principle as a accountable factor there, and we will discuss that how this happens. Okay, so uh, first of all we found out these two things for the identical particles. Where is that topic? Symmetric and antisymmetric. There is spin, then the Stone garlic experiment, then the symmetric and antisymmetric. Yes, here is symmetric and antisymmetric wave function. And so let's have a little discussion or the recap. So we have already seen that for the identical particles, two kinds of wave function are possible. First one is symmetric and second one is symmetric and antisymmetric, right? Let's have for example the complete wave function psi for n number of particles, non-interacting particles, and they are non-interacting particles, can be expressed as the product of all the wave function of individual particles. Like for example, if I need to write the total wave function of the system of n particles, and they are identical particles, they may be distinguishable or indistinguishable. I mean, they may be non-identical or identical. In always for n number of particles, if you need to write that combined wave function, then you need to find out the individual wave function of every particles, right? For every particle you need to find a wave function of wave function of individual particle, and then you combinedly by multiplying them you can write the total wave function. But our discussion is only for the identical particles. So the total wave function will be somewhat like psi 1, psi 2, psi 3, phi 4, and so on, and phi n. Okay, however Hamiltonian is was the can be written in the additive formation. So now for example, if we have two particles, let us consider two particle system. Suppose one of the particle is in A state and other one particle is in B state. So we found out that if for example we have two particles, n is equal to 2 here. Okay, so the total wave function is, and suppose for instance we have first particle in A state, A eigenstate, second particle in B eigenstate. Okay, so I can write my wave function as, so if the particle 1 is in state A and particle 2 is in state B, then the wave function would be something like psi of 1 and 2 will be somewhat like psi A1 and psi B2. Okay, now because the particle are indistinguishable, now this can be our wave function. Okay, but how do I know that this particle is in first state and this particle is in second state? Because my particles are identical in nature. So if I cannot distinguish them, so I can have a second probability or second probabilistic case in which the wave function can also be written as somewhat like a second type kind of wave function, in which where I assumed in the last case, when I assumed that the first particle is in A state and second particle is in B state, but I don't know which one is the first particle and which one is the second particle. So any of them can be in A state and any of them can be in B state, right? So there can be two possibilities of the arrangement, and the second possibility is that that second particle is in A state and first particle is in B state. Now for instance, I have a infinite potential well, for example. Now in infinite potential well, one dimensional infinite potential well, you know that the wave function is somewhat like √2 wave function of nth state is equal to, now this is a antisymmetric or asymmetric potential well, and this is distributed from x is equal to 0 to x is equal to a. Potential is inside 0 and here potential is infinite. So you can write the wave function of particle in nth eigenstate is equal to √2 by a sine n pi x by a, right? And energy eigenvalues are corresponding to nth state is n square pi square h cut square upon 2 ma square, right? Where n is equal to from 1 to 3 and so on. N is equal to 1 is the ground state, n is equal to 2 is the first excited state, and n is equal to n is the n minus 1 excited state. Okay, so now suppose for instance, for the ground state wave function, if I make the ground state wave function, now this is the ground state wave function and this is the first excited state wave function, right? So I have two particles, two identical particles. For two identical particles, if I make the energy levels, now this is for n is equal to 1 and this is for n is equal to 2 and for n is equal to 3, don't bother about the gap between them, because gap depends on the the gap between n is equal to 1 and n is equal to 4 is 3 e naught. Here the value is pi square h cut square upon 2 ma square, and the value of first excited state is 4 pi square h cut square upon 2 ma square, and the gap is somewhat like 3 pi square h cut square upon 2 ma square, and for the next term this is near about 4 pi square 5 pi square h cut square upon 2 ma square. So don't get bothered about this gap. Okay, in the representation don't get bothered about this gap. This arrangement of line can be maybe in, okay, leave it. So I have two particles. Now for two particles, if one particle is here and second particle is here, so for first particle my wave function is this one, and for second particle my wave function is this one. This first particle is in first ground state and second particle is in first excited state. And second case can be that this particle, because these are identical, I cannot distinguish them by using different color of pencil, that this particle is second and this particle is first, red particle is second and green particle is first. So I cannot distinguish them actually using these things. So there can be two possibilities, that this particle we are using here, this is second particle and this is first particle. Now I assumed that this particle is second, this particle is first, but it can be somewhat like this also. It could be somewhat like this, that this particle is first particle and this is second particle, and by exchanging them, so or we don't have any probability density variation by after exchange and before exchange. We got that the probability is same, probability density of the is same of the whole complete wave function. So I got two different scenario, two wave function from here, one for the symmetric case and one for the antisymmetric case, and the combined wave function I wrote that combined wave function is something like psi a1 psi b2 plus minus psi a2 psi phi, you can write phi, okay, that's then phi would be a good representation of this, phi b1, okay, symmetric and antisymmetric or plus minus. And for normalization constant you can write like can apply a normalization constant after normalizing this wave function. So for symmetric wave function, I have my wave function as somewhat like this. My writing is not so good on pad, so psi a1 psi b2 plus psi a2 phi a1, okay, these are phi. And for antisymmetric case, antisymmetric wave function, this is 1 upon rho 2 phi a1 phi b1 2 minus phi a2 phi b1. Then from here we computed that there is a Foley exclusion principle which says that for antisymmetric for these kind of particles which falls in the category of antisymmetric wave function having antisymmetric wave function, they cannot be in the same state. If they are in same state, then I can compute, or I can write, if we set a and a is equal to b, then this summation would be equal to 0. If a is equal to b, then my total wave function for the antisymmetric in this case would be 0. And from here Foley actually stated that for any two fermions or for any two fermions we need to choose different eigenstates. Okay, now I will take a particular example to distribute two particles in one dimensional box. I will do for bosons, and you need to study by yourself for fermions. Okay. So suppose I have two bosons. Just have you know them, and you know that the bosons follow the symmetric wave function. I will arrange boson in the ground state and excited state. I will look that how the particles follow the total wave function. So now I am taking a particular case where I have two bosons. Now spin is not when spin is